Welcome to this fifth class about goal conditioned reinforcement learning. This time we will see the notion of curriculum. So first a few words to define what we mean by curriculum. So the idea of a curriculum is to define a sequence of goals, in the case of this framework, behavioral goals, to maximize some learning measure. And the point is that the learning measure can be different depending on the framework. For instance, it can be coverage. In the case where you are interested in reach the whole goal space, that means maximally expanding the set of achieved goals. You may want to reach these goals at least once without necessarily mastering the way to go back to them. Another approach is competence. This time you want to consistently reach some desired, eventually hard goals. This is what I illustrate with this. Reaching that particular goal probably requires a curriculum where you first learn to ride a bike and then a more complicated bike and finally a motorcycle. And the third possibility is to try to maximize what we call success coverage in this paper. And that means consistently reaching the whole goal space upon request, which is doing both this and this. So in this video, I will split the literature into two parts, those which try to maximize coverage and those which try to maximize competence. But before going into the separation, I will first build a few intuitions from some preliminary remarks. So let's start with a very simple framework, which is called goal exploration processes, that does not have a goal condition policy, but just a population of standard policies. In goal exploration processes, you want to reach as many goals as possible into some goal space, but for that you have a set of policies. And one point that is very important is that if you draw a large set of policies, only a few of them will do interesting things. Most of them will do boring things. Okay, if you start from there, probably most policies will stay in that corner. And what's interesting is to sample in that particular part of the policy space. To do this, the goal exploration process algorithm favors sampling the interesting achieved goals as follows. First, you sample a random point in the goal space, for instance here, and then in the archive of policy or the population of policies, you find the nearest achieved goals and you select the corresponding policy parameters. So if you were sampling here, probably the nearest achieved goal is that one, and then you will sample here, which means that you will sample in the area that is interesting. Then you perturb the policy parameters theta into some theta prime that is here, and probably you will get a different interesting outcome. So that's a very efficient way to sample in the space of policy parameters that correspond to interesting outcome. And the idea is that if you do this consistently, what will happen is that you will often sample at the border of the interesting achieved goals. Okay, see if you have achieved those goals, probably your policy parameters will be close to these ones, and you will discover little by little areas that go beyond and beyond the boring outcomes. This point is explained in that particular paper. Now let's transpose to goal conditioned reinforcement learning. This time we don't have anymore a population of standard policies. We have just one goal condition policy, which is conditioned on a behavioral goal and that provides some achieved goals. And we also have the same setup as previously, but now we have behavioral goals, okay, that we can sample as we want, and some desired goal. Again, for many behavioral goals, your policy will provide some boring goals, and we have to consider the mapping between the behavioral goals and the achieved goals. And as I told you in a previous lesson, we would like this mapping to be the identity, so that when we set a behavioral goal, we get the corresponding achieved goal. So the idea is that the way to obtain this identity is to expand the behavioral goal distribution by going beyond the achieved goal distribution. So we want to expand the set of achieved goals so that it corresponds more and more to behavioral goals. And to do this, many goal conditional reinforcement learning also sample at the border of the currently achieved goals, so as to slowly improve the capability of the policy to reach the required behavioral goal. And one point is that reinforcement learning and insight experience replay, which is an algorithm that we will see on the next lesson, contribute a lot to improving the mapping, and that's particularly the case of insight experience replay. Now let's go for a different intuition about the difficulty of setting the right curriculum. So we consider an environment like this where we have what is called some bottleneck. It's hard for the policy to go through those corridors to discover these places. In this paper, Campos shows that some achievable goals may never be discovered if you train your policy while you are exploring, because the training process will make so that the agent may prefer being rewarded on goals that it already masters than discovering new goals that it won't be able to reach again and again. So from one side, you may not want to train while you are exploring. And in particular, these authors propose to first explore and then only learn. But on the other side, the point is that some goals that might be achievable may not be discovered if you don't train. This is the idea that some goals are difficult to reach and you need to reach some stepping stones before going to them. And this point is rather made in this paper from Adrien et Coffey with the Goal Explore system that I will speak about again later in this class. Now let's go for the presentation of a few algorithms. So first, some methods doing some curriculum based on coverage. One important paper in that category is the intrinsic curiosity module. That's this paper where the agent is rewarded for reaching states that it poorly predicts. So it has some model of the environment and it tries to predict the next state, and when the next state is poorly predicted, it means that where you are you don't know very well, so it corresponds to less seen states. And that's a category that we call knowledge-based intrinsic motivation. It is used in addition to reward to favor exploration. So the goal here is to explore a lot, so to reach as many goals as possible and choose to maximize coverage. But note that in this paper, this is not a goal condition policy. You just have some intrinsic reward in addition to the standard reward. So it cannot truly be defined as a curriculum on goals. A follow-up of the previous paper is the plan to explore paper. That's this paper. What they do is that they also have some models to predict next state. But the point is that they have several models and they use the disagreement between the models to decide to reward or not, to provide some additional intrinsic reward for the given state. So in intrinsic curiosity module, you have an exploration issue because you need to visit the state to figure out whether they are poorly predicted or not. Whereas in plan to explore, since you have the models, you can play in your head with your models and discover that they disagree without going to the state to see whether you predicted correctly or not. The fact that the different models predict different states is enough to know that you don't know this state very well without having to go there in practice. But the point is that with these two algorithms, intrinsic curiosity module and plan to explore, you suffer from what is called the noisy TV problem or the white noise problem. The idea is that the agent will be attracted with what it cannot predict, but if you have some states in the environment that are not predictable at all, then the agent will get stuck in those states. And note that plan to explore as intrinsic curiosity module is still not goal condition. It's still using an additional intrinsic reward, but with a standard policy. So let's go back to the noisy TV problem. To understand this problem, you have to distinguish between what is called epistemic uncertainty and aleatoric uncertainty. With intrinsic curiosity module and plan to explore, what you target is epistemic uncertainty. You say that the agent cannot predict correctly some next state because it does not know enough about these states. But in the environment, you may have what is called aleatoric uncertainty. For instance, a noisy TV screen produces aleatoric outcomes and the agent cannot be good on predicting those things. So an agent focusing on surprise may get stuck in front of white noise, so it just should target epistemic uncertainty and not aleatoric uncertainty. And I will show you in the next part of this lesson that approaches based on learning progress can fix this white noise issue. So that's the second category of systems. That's the system where the curriculum is based on competence and not on curiosity or coverage. So this approach is clearly formalized in this paper author from Manuel Lopez and Pierre Oudeye. So the idea is that formalize exploration as playing with a set of bandits, and you may have different bandits providing different rewards, and playing one arm is the equivalent on trying to achieve one particular goal. If you target goals that are too easy, you won't make any progress because you already know to do them. So if you are already an expert, you cannot make any more progress. So you should avoid to try bandits that are too easy. But on the other side, you should also avoid to sample bandits that are too hard, because you won't make progress on them just because it's too hard for you to make any progress on those goals. So the idea is to try bandits where learning progress is the fastest. So if you sample the goals where you are making a lot of progress, you will progress a lot in these goals, and then probably this progress due to transfer learning will propagate to harder and harder goals. So probably your agent will start from very easy goals and move slowly towards more and more difficult goals. And that's called competence-based intrinsic curiosity. The idea is that you use learning progress instead of exploration or coverage to organize skill acquisition. And you can see that it escapes the noisy TV problem, because the noisy TV problem is always too hard. You cannot make progress on that particular goal. So you will stop sampling that particular goal. If you use a curriculum based on learning progress, probably you will have these kinds of output figures. So the idea is that here you have different tasks that are organized by harder and harder difficulty. Task 1 is easier, and then task 2, etc. And here you have the performance of the agent on those tasks. And you can see that, of course, the agent gets very performant on the first task very soon, and then on the second one, etc., etc., as long as they get harder and harder. And here you have the learning progress on those tasks, and you can see that the agent makes a lot of progress on the first task, then the progress becomes low, so it starts sampling more the second task, and then the third, etc., etc. And also an idea is that sometimes, due to sampling other tasks, you may forget about doing an intermediate task. That's what you see here, where the competence of the agent on task 3 is getting low. But if you use some absolute value of learning progress, when the learning progress is decreasing a lot, you get a bump in the absolute value, which makes you sample again this goal, and you will recover your capability very soon. That's what you show with these graphics. So you can see that using learning progress will generate a curriculum in the order of a growing difficulty, which is quite interesting, because this is what will maximize the competence of the agent. I also told you that catastrophic forgetting here generates new training on the goals that you are forgetting. And one point is that with this system, exploration is more in the solver, not in the setter. So these systems are not based on exploration for sampling goals. They are just using the learning progress. One point is that since you don't explore much in terms of goals, finding new regions may result in adding new bandits and requiring more exploration. Finally, I wanted to show you this slide about the Go Explore system. That's the system that proposed to reach again some stepping stones that allow you to discover new areas. Okay, and in this diagram, in their Nature paper, they show that here you have the performance on Montezuma's Revenge through time, and in the beginning the performance was very low. Here you have the average human performance. You started to do better than this around 2018, and then here you have the expert performance. Here you have the top reinforcement learning agents like Agent 57 or Never Give Up, and they show that with Go Explore they go beyond this, and when they add specific domain knowledge related to the particular game, then they can even beat the human world record on Montezuma's Revenge. And that's it for this lesson. Thank you for listening, and as usual, I just show you the next slides so that you have a look at the bibliography.